Good morning, everybody. Today I'm going to do the lecture 5 of the series on analytical methods. I'm going to have a slight change in pace in this lecture. The first, or rather the first 1/3 of the lecture will be on analytical methods, and I made improvised and then decided to talk a little bit about experiments, or the experiments we do on jet fuels. So that would be the other, perhaps the half or maybe the 2/3 of the lecture. So the first part would be the analytical methods, and the second part would be experiments. Okay, so that's the plan. All right. Okay. All right. Today I'm going to talk about rate ratio asymptotics as applied to non-premixed flames. Okay. Before this is just a brief summary of what was done yesterday. We looked at aspects of, so these are just a summary of what was done on activation energy asymptotics. Essentially what it is that in activation energy asymptotics, as I said, the chemical reaction is approximated by a one-step process, fuel plus oxygen going to products, and that's the rate constant. The key assumption here is that the activation energy, which is the ratio of E over R, that's the activation temperature, this is large. So that as a consequence, because that's large, as a consequence is a Lawich number, which is again constructed from this activation energy, that's large. So this is the central assumption. To a one-step reaction, large is a Lawich number, right? And then we also looked at analysis in the limit of large values of the Damkohler number. Here's this quantity beta. And then the beta again is related. So here you have there's a Damkohler number that's large, and there's an activation energy. So this quantity beta is of course related to Zel'Zovich numbers. That's why so the analysis that I described yesterday was done for large Damkohler number as well as large activation temperature. But we looked at the distinguished limit. So although these quantities are large, we said this particular so here's the distinguished limit. So this is so the analysis was done in this distinguished limit because the denominator is large, the numerator is large, but the ratios of order 1. Okay. So and I pointed out that one of the serious limitations of activation energy asymptotics is that there's fuel. There are many, and this is one of them. And it's that the reaction zone, fuel leaks through the reaction zone. Okay, that was the limitation. And then, so that's that's good. But it does give a scalar dissipation rate at extinction. But this is the drawback. So now I'm going to show you how this drawback is removed by considering rate ratio asymptotic analysis. Okay, right? Okay. And the reason why how does this way here? Oh, okay. And the reason why that happens is that if you look at the flame structure, for the diffusion flame structure, this is in terms of the mixture fraction. This is Z equals 1. This is the fuel side. Z equals 0, the oxidizer side. Usually it turns out that the stoichiometric, the flame sits very close to the oxidizer boundary. So this is where the flame is, very close to the oxidizer boundary. Therefore, you have this temperature profile here, and there's, of course, another temperature profile here. Okay, so you can see that the gradients of temperature on this side is very sharp because this, in fact, this term for most hydrocarbon flames, this is like 0.05. Okay, so you can see that this temperature gradient is very large. So if you have a fuel which comes in, because there's a rapid decrease in temperature, what happens is that the fuel actually leaks through the reaction zone because of this rapid decrease in temperature. And since the activation energy is large, it causes the fuel to leak. Whereas on the other hand, oxygen does not leak because the gradients of temperature on this side are not as steep. So therefore it's possible. Therefore, the oxygen is completely consumed, and the fuel leaks for that reason. Because of the sharp gradient, quickly freezes chemical reaction and leads to leakage of fuel. Okay. All right. So here, this is what I'm showing you right now. So here, these are numerical calculations of a methane flame. This is done with using detailed chemistry, and this is plotted the profiles of methane, hydrogen, oxygen, H radicals, okay, are all part. So this is a pure diffusion flame, okay. Again, numerical computations using detailed chemistry, and the profiles are plotted as a function of the mixture fraction. All right. Now here's something interesting to notice here. You can see that the numerical calculation show that there's methane, okay, and then you can see that the H. So you can see that the H radicals reacts with the methane. Okay, so this is, I've not, and forms CO2 and H2, CO and H2, and which I have not shown here. Okay, so now you can see the radicals reacting with the methane. But what is interesting is that you can see that the oxygen leaks through the reaction zone, whereas the fuel is completely consumed. Right? This is the reality. Right? So there's complete consumption of fuel, leakage of oxygen. Right? Whereas this is again, this is numerical calculation using one-step chemistry. If you do with one-step chemistry, you notice that numerically there's leakage of fuel, okay? Whereas it is the oxygen that is completely consumed. And it turns out that this plays a very important role when you try to model partially premixed flames. This leads to completely erroneous trends, right? Unfortunately, I won't have time to talk about that. But so you can see that there's a real qualitative difference, okay, with one-step chemistry and detailed chemistry. All right. Okay, so now I'm going to start out with the reduced scheme, which I talked about yesterday. So the rate ratio asymptotic is going to be done with this four-step mechanism. Now, and that's very interesting because if you look at one-step chemistry, the overall reaction rates for premixed flame and the overall reaction rates for diffusion flames will be completely different. Okay, because these are global reaction rate parameters. Even though you have one-step chemistry, what works for premixed flames will not work for diffusion flames. On the other hand, rate ratio asymptotic analysis, which uses reduced chemistry, the same. This is what we used for premixed flame, and it applies to diffusion flames as well. Okay, right. Now, as I mentioned yesterday, these are the global rates, and the principal elementary reactions that contribute to global rates are given here. So these are the two rates which contributes to this global rate, okay, as you've seen here. For this global reaction, it's this elementary rate. Okay, this goes backward and forward, right? And then this is the chain termination step, and this is the elementary reaction for that, okay, and 8. Because this is also chain termination, correct? Because CH3 reacts with H to go to CH4, so therefore that appears here. And that's the chain branching reaction, okay, right? Okay. Right, so now these are all, the rest is somewhat mathematics. So now, and I talked about this before. Again, you introduce a conserved scalar quantity called the mixture fraction, and I talked about this yesterday. And then that's pretty much what it is. I mean, this is actually, that is the C, and I've used the Greek C instead of the Z, okay? And it is such that Z equals 0 in the oxidizer stream, and Z equals 1 on the fuel stream, okay? And as I said, this important quantity that appears in analysis of the non-premixed flame structure is this scalar dissipation rate. And the scalar that's given by, and it has units of 1/2. Therefore, it is the reciprocal of a characteristic residence time, right? And then again, it's a lot of details. I mean, you define a xi. So this is actually xi is actually the mass fraction, right? A non-dimensional temperature. That's a non-dimensional temperature. A normalized mass fraction. Even though I put an xi, it's actually a function of yi. It's actually yi. You can rewritten in this form. And it turns out that if you write x, this is close. See, this is close to the mole fraction of the fuel, of the mole fraction, because the average. So the WN2 appears. You see this. If in the combustion mixtures, the average molecular weight of the mixture is very close to that of N2 nitrogen. So therefore, even though this is a normalized mass fraction, this is actually very close to the mole fraction. Okay, so it's not the mole fraction, but it's very close. Okay, and that's the temperature, non-dimensional temperature. This is stoichiometric mixture fraction, ZST. That's where the flame is located. Okay, right there. All right. Okay, and this is a quantity which is actually the gradient of oxygen. We shall see that later. Right? Okay. Now, the flame structure again, as I talked about before, it's made up of two layers: a convective diffusive layer, which is the outer structure, and a thin reaction zone, and a thin reactive diffusive layer, which is called. So therefore, there's an outer structure and inner structure. So this is where it's chemically reactive. Chemically inert, and all reactions take place in this thin layer, right? And the thickness of that is of order epsilon, the thickness of the inner structure. Okay, all right. Now I'm going to just show you briefly what the structure is going to look like. See the there we go. Okay. So here you have. So this is the outer structure. So in the outer structure, there's this thin flame sheet, and then you have that's a temperature profile. Okay. So this is how the outer structure looks like, and this is so this region, which is the outer region here, and this regions are frozen. Okay. This is Z equals 1, Z equals 0. So we in the outer the species that appear in the outer structure are CH4, which is O2, H2O, and CO2, and temperature. That's it. So because the outer structure is governed by a one-step reaction, basically. So these are so all these species appear in the outer structure. Okay, none of the others. Then you go into the what's the inner. Then you look into the reaction zone. So if you look at the reaction zone, again, it's made up of, as I talked about yesterday. There are two layers. There's a thin fuel consumption layer, which is of order delta, and there's an oxidation layer, which is of order epsilon. Okay, so that's the overall structure, right? Okay. Okay. And as I said, in the outer structure, as I just mentioned, only the quantities of fuel, the carbon dioxide, H2O, only these things appear. Okay. So now here is a key thing that we do. I mean, if you recall, yesterday I talked about this Lignan's Lignan's premixed flame regime analysis of Lignan. I talked about that yesterday. Okay. So the key point of the analysis is because we find that the oxygen leaks through the reaction zone in the outer structure, such that this is the flame temperature, okay, Tp, and then if you look at the profile of O2, this represents O2 leakage. So I prescribed that the flame is over here, right? So and it is positioned such that there is some leakage. So leakage. So this is like Lignan's premixed flame regime, where one forces leakage of oxygen through the reaction zone. Okay. Now, because not all the oxygen is completely consumed, it turns out that the maximum temperature that you have here, the maximum temperature Tp, is less than the adiabatic temperature. So this TST, okay, is the temperature when oxygen is completely consumed. For example, if oxygen were completely consumed, so the flame will be somewhere over here, okay, and they will result in complete consumption of oxygen. Because there's leakage of oxygen, the flame now sits over here, and does not reach the complete adiabatic temperature. It's less, and there is a leakage of oxygen. Okay. Okay. So again, I want to point out that when oxygen leakage is 0, there's no leakage of oxygen. Then this Cp, the flame position, will be equal to CST, and the Kp, the flame temperature, will be equal to the adiabatic temperature. Okay. Right. Okay. So so this is only these equations. I'm not going to. These equations tell you again. It's a base. Okay, what I've done here. These are element balance. So, these are, you can see that this is balance. So this particular. So assume Lewis number 1. Okay. Now, since elements carbon, hydrogen, oxygen are consumed, this simply tells you, except that's a fuel that has 1 carbon. CO2 has 1 carbon. Okay. So that's the conservation of the element carbon. This is the conservation of element hydrogen, because CH4 has okay, that's the second one. Yeah, that's hydrogen, because CH4 4 hydrogen CO. Okay, and 2 hydrogens over here. So of course, there must be a 4, there must be a 2. That means there'll be a 4 over there, never divided by 2. Okay, so this is a conservation of element hydrogen. This is conservation of element oxygen. Okay, and this is energy conservation equation. So this is it. This is all you need to write down to construct the outer structure. Okay, and that's, so if you solve this set of equations, and then one can, and the other prescription is that the other thing you need to do here is to say that there's at CP, CH4 goes to 0. Okay, and then you prescribe the leakage. You see you pick a value for the leakage. Okay, but you do see that is equal 0. Okay, yeah.
Question: what controls the value of O2 at position P? How does that scale?
Okay, how does it scale to what? I mean,
Donsel number?
Yeah, yes, it does. What it is that you pick a value. Okay, you pick a value of oxidizing leakage, and then this is the outer structure. But then you go into the inner structure analysis of the inner structure, and the inner structure will tell you what scalar dissipation rate corresponds to that as the PCP. It's like the inverse problem, So you pick one and you get the other, right? Yeah. Okay. All right. Okay. So again, I think I may have said that here. Note that it's presumed. Okay. For given values of TP, the values of CP, this all I calculated. Analysis of the inner structure, I pretty much answered that question. Analysis of the inner structure will give the corresponding value of the scalar dissipation rate, which is consistent with that selected value of XO2P. Okay, that's the point. Okay. Now for convenience, I introduced these definitions are introduced again. So now why it turns out that if you look at in the flamelet formulation, right? I mean the loose number appears in the diffusive term. So it's always convenient just to define a new variable with the loose number. Okay, so that loose number is kind of lumped into the conservation. So that's the reaction rate, heat release. So this is the heat release for each of these reactions. For example, each of the 4 steps that I talked about. Okay, here. Okay, or this is maybe I'll continue on. Okay. Now this is the heat release in one of the global steps. This is the overall heat release, and that's what QK is. Okay. All right. The other thing we have said that we are assuming that the scalar we evaluate the scalar dissipation rate at psi p, and then of course small changes in the reaction zone is neglected. Okay. All right. Okay. So these are the so that's the outer structure. The outer structure has been constructed. Okay. We know what the outer structure is, right, based on element conservation and energy conservation equation. All right. Okay. Now we're going into the reaction zone structure. So this is these are the species balance equations, right, in the reaction zone. Okay. So remember, okay, here's what I want you to get here is that. See, if you look at the number of species, we had many more species, correct? We had CO2, we had many more species, but it turns out only actually we had 7 species, right? But it turns out that because it's a 4-step mechanism, right? That means there are only 4 independent species balance equations I can write. Okay, for the other species, you can get that from element balance. Okay, correct? So therefore, these are therefore to solve the complete problem, it's required only to solve these 4. So the 4-step model, what that 4-step model simply means is that there are 4 differential equations you have to solve. Okay, all right, that's the point. Okay, so therefore we have now 4 differential equations. Okay. And the remaining species in the reduced mechanism, here you can see that. So the remaining species, so these are the coupling relationships. So for example, if I want to know, here you don't see O2, but if I want to calculate OP, I get it from this coupling relationship. Okay, you see that, right? You get it from here, and then there's another coupling relationship. So if CO2 doesn't appear here, you get it from this equation. H4 doesn't appear here, you get it from that. okay, and so on. And that's the energy. So also what's not required here, you don't need to solve, you don't have to look at the energy, the equation for the temperature, right? Why is that? Because, again, because of energy conservation. Okay, that's also another coupling relationship. So that's it. So once you solve these for all the concentrations, okay, well, fuel, hydrogen, carbon monoxide, and hydrogen, you get that by solving these differential equations. Everything else is obtained by coupling relationships. Okay. Right. Okay. Now, now I talked. So this is the inner structure, the reaction zone structure, and you can see that there is the reaction zone is made up of two layers. This is the inner layer, which is of order delta, and we saw yesterday that in the inner layer, the fuel-specific reaction, which is the CH4 plus H, and the chain branching reactions take place. Those are the only two reactions that take place in this layer. And there's this oxidation layer where the other reactions take the other. Okay, here in this reaction, H2 and oxide. So basically, here's what's happening here. This is methane, reacts with hydrogen. So that's the first step. Okay, and it forms H2 and CO. So that's the first. So that's, but okay, the H2 and CO, even though they react, the changes here are not very large for H2 and CO, and H2 and CO that are formed in this layer are now react in this oxidation layer, reacts with oxygen. Okay, in the oxidation layer, this reaction between H2 and O2 and CO-O2. But of course, because it's actually the radicals, it reacts with the radicals. So that's where the consumption, and also it turns out that the radicals are formed in this layer, or the formation of radicals. Okay, radicals are formed by the H2O2 reaction. It goes back, reacts with. So that's the structure. All right. Okay. So radicals, therefore, they are present everywhere due to finite rate chemistry. Okay. Now, the other thing I want to point out that even in this diffusion flame analysis, I've spent quite a bit of time yesterday talking about this inner layer temperature, okay, being a fundamental property of the premixed flames, right? The inner layer temperature, which is obtained by crossover, it's a crossover temperature between chain branching and chain termination reactions. The same thing happens here as well. There's this inner layer temperature T0, okay, which is obtained from which is a consequence of between branching and termination reactions, okay. So again, that's the same T0 appears here as well, okay. All right. Okay. Yeah, I want to take. Are there any questions on this? Because on the inner structure, yeah. Yes. Yeah, because of finite rate chemistry, the maximum allowed temperature is but if you assume that the reaction rates are taking place at infinite rates, okay, right? Then the maximum temperature is Tp, but the chemistry is taking place at a finite rate. So therefore, it's lower. Okay.
How different is that temperature?
It's of order epsilon. That's where it's the mathematical answer. You see because the thickness of this layer is epsilon, correct? And so the temperature decrease in temperature from the maximum temperature is of order epsilon. Okay, right? But and then we shall see what that epsilon is. And it is small. It's not that, but it's a small quantity. Okay.
Is there any relation between the mixture and gas?
And what?
Any relation between mixture fraction and eta?
And eta. No. This is an independent variable. Yes, there is. This is a stretched coordinate. Okay. So this is a stretched. So this is it's C minus CST divided by epsilon. That's what that is. Okay? So we shall see that later. It's eta. It's going to be Z minus ZP, rather. Okay? Because that's the flame position. So maybe I should put the Greek over epsilon. Okay, so now and I want to say a few more things here, just qualitatively, because the rest is all math, and one can get buried away from the mathematics. You see what it is so now we can look at the order. What order should these various species be? Okay, Now we can see that H2 and CO are oxidized in the epsilon layer, the oxidation layer. So therefore, it will turn out that H2, X of H2, therefore X of H2 will be of order epsilon because it is consumed in the epsilon layer. X of CO will be of order epsilon, okay, and X of O2 will also be of the order. Well, X of O2 because here we have assumed that X of O2 is of order 1. Okay, so these are the two. So these two quantities, X of H2 and X of CO, are of order epsilon because the thickness of this layer where they react is of order epsilon here. Okay. Now, if you look at CH4, because it is the CH4 reaction is taking place in the smaller layer. Okay, so the CH4 is going to be of order delta. So CH4 or X of CH4 is of the order delta. And then of course we have made the assumptions that delta is much less than epsilon, much less than unity. Okay, so that's the right. Okay, so what does that mean? So what it means is that when you analyze the structure of this layer, okay, when we're analyzing this fuel consumption, the reactions that appear will depend on H2 and CO, but then we can simply write the H2 and CO as but we can neglect the changes of that in this layer of H2 and CO, okay, because it's of a higher order, because epsilon is greater than delta. One can neglect the changes of H2 and CO in this layer. Okay? So in this layer only H and CH4 change, all right? And in this layer CH4 is 0. Okay, there's no CH4 there as well. Okay. So I mean these are again these are okay. So the rest is again it's all details. So again I've said that what I just said before, I just said it again. At the reaction zone, the concentrations of O2, CO2, and H2 of order unity. Okay. So again, I can say that. Okay. What it is that in the reaction zone, okay, remember that O2, CO2, and H2O were obtained from the outer structure, correct? Their values. So therefore, they're of order unity. All right. So therefore, this is the concentrations of these things are much larger than H2 and CO. Okay. All rate constant. All right. Okay, so that's it. Okay, all rate constants about. The other thing I want to show you that because it's rate ratio asymptotics, since the activation energy is not large, okay, we can neglect the change. The reaction rates, of course, depend on the temperature. We can neglect the changes in reaction rates with respect to temperature because activation energy is not large. Only if the activation energy is large, you have to worry about. Then it's sensitive to temperature. Here it's not sensitive to temperature because activation energy is not large. All right? Okay. So inner layer is of thickness that. Global step 1 and 4 are the main reactions in the inner layer. Okay. Fuel is completely consumed in this layer, and the main compounds form the CO and H2. I just said what and this is the oxidation layer, thickness epsilon, and the global step 2, 3, and 4 are the main reactions. This is identical to what I talked about yesterday, right? For the premixed point. There's no change, basically. Okay, all right. Okay, so now, normally the way you do that is you go smaller and smaller. You analyze the outer structure first, which is the largest one. Then you analyze the next one, which is epsilon. Then you go into the inner structure. Okay, go backward this way. So here's the outer. So this is the epsilon layer. In this layer, the concentration of fuel is small. Okay, so therefore, so we can get rid of two of. It allows us to neglect the first reaction, which is CH4 plus H. It's not taking place, all right? And also we make a steady state approximation, right, for H. So once you make a steady state approximation, but because CH4 is not there, you have only a 3-step mechanism. Because H radicals are in steady state, it goes down to 2, okay? So these are the only 2 reactions that take place in the oxidation layer, okay? So these are the described equations. So for the 2 reactions. Again, I did not write oxygen, even though oxygen is consumed, because oxygen you get from coupling. Okay, right? Right. And this is the Damkohler number that appears here. That's the Damkohler number, right? And this quantity S is a detail. In other words, this quantity S is. Remember that I said that in the oxidation reaction 2 and 3 take place in that layer, okay? So this quantity S is the ratio of the Damn-Coulomb number of the second reaction to the third reaction. So it's the ratio of these two Damn-Coulomb numbers. Now, again, one can again look at some limits. For example, you can say what happens when S is large. So that means D3 is much smaller. So that means the rate of this step is much smaller than the rate of that step. Okay, that could be okay. Or alternatively, you can have S small. Okay, so S is small. Of course, that means D2 is much smaller than D3. So in that case, there will be a further simplification depending on what limit one imposes for these two Damn-Coulomb numbers. Okay, but in this analysis, we found that it's actually these two Damn-Coulomb numbers, D2 and D3, are of the same order. Okay, so therefore those two limits are not applicable. Right? Okay.
The first equation is independent of D.
Which one? The first?
D squared.
This
the
one
mole
here?
fraction of CO times, yes. Because since it is proportional to D2 by D3, S is proportional to D3.
Yeah, it is actually, it's, and the D3 appears here, okay?
Yes, okay.
But that's just because of the, if you look at this particular equation, I mean, if you look at CO, if you add CO and H2, okay? So you just, if you look right, the conservation, if you write for CO, all right? It's for CO is W2, all right, okay? And for H2, if you write, let me just do that. It's a, okay, so if you, okay, so now if you look at the second D squared XCO, DC squared, okay? If you look at that one, that's going to be W2, right? That's it. Okay, we'll do this. And if you look at D squared H2, DC squared is going to be, that's, okay. So that's going to be 2W3, correct? Minus W2. Okay? And if you add them up, the sum, which is D squared DC squared, is H2 plus CO. Okay? Sorry, H2 plus X of CO. The sum should be equal to 2W3. Right? Okay? So that's the point. All right? So just for convenience, I mean, I could solve these two equations, but it's more convenient just to add them up. All right? So there's only one source term on the right hand side. There's only one source term over here. That's just convenience. Okay? All right? Okay. I'm going to go through quickly of this one. All right. Okay. So that's the. So those are the two reactions. Okay. Okay. Anyway, so these are just rewriting the whole thing. Okay. Now again, I just said that there are two limits: S large, S small. So now these are the expansions in the oxidation layer. This answers your question. What is C minus CP? It is eta. Okay. Remember that I said XCO is of order epsilon. So that's the expansion for. So here ZCO is of order unity. Okay. XCO is of order epsilon. XCO plus, I write the sum. The sum is also of order epsilon, okay, and XH to this. Now the small, now you select the small, because of the large Damn-Coulomb number asymptotics, D3 is very large. The small parameter is chosen such that epsilon is the minus 2/5 power of the Damn-Coulomb number. So when you do that, then these are the two differential equations you get to solving the structure of the oxidation layer, okay? And these are the boundary conditions. Now it's possible to integrate these sort of equations, all right, subject to these boundary conditions. And the idea is that from the integration, you can get the profiles of CO and profiles of H2, okay, basically, all right, okay. Okay, so this is equations. Yeah, again, even though these are, one can, if you want to solve them analytically, if you say, for example, S is large or S is small, there's an analytical solution to that, okay? But now, since I'm solving them coupled differential equations, it has to be done numerically. Okay, now this is the profile. So here you can see the profile of H2 obtained from numerical calculation of all those two differential equations. All right? Okay. Now, what is required? What is really required is that what we want to know is the value. See, this is where the this is the where the inner layer is, right here, where the fuel consumption is taking place. Remember that H2 and CO are formed in the fuel consumption layers, therefore the profile goes to C. So the fuel consumption layer is right here, and then this is the profiles. Okay, so it turns out that it's a detail. It turns out that you need to know these values. You need to know the values. So another thing what I show here is that S is so S1. That means that both the Damkohler numbers are of the same order. S5 is this is large Damkohler number. This is the small. It's for small values. So it just tells you how how the profiles will look like depending on what the value of S is. Okay. All right. Okay. So this is again, this is something which this is what is required. So, right. Okay. So let me just skip that one. All right. Now we go to the that was the analysis of the oxidation layer. Now we go to for the analysis of the inner layer. Okay. It's a bit complicated because many reactions appear. So I don't think I'm going to go through. Anyway, so you can see that this is the fuel. This is H radicals. All right. So I think that these are anyway. The point is these are the equations that describe the structure of the fuel consumption layer. All right. Okay. Now to analyze the fuel consumption layer, you introduce these following expansions. Again, there's a delta. Remember that this is an independent variable zeta, and that is expanded with delta. Okay. Previously it was expanded with epsilon. Then we are looking at the oxidation layer. Here we are looking at the fuel consumption layer, where the fuel consumption is taking place. They're all of order delta. Okay. So that's and here this is R naught, but R naught is of the same order as delta as well. Okay. So this is the final equations that you get to solve the structure of the inner layer. And again, you have another, and I talked about this yesterday, there's a parameter omega that appears. This omega, we can again look at limiting values of omega. You can say what happens when omega is large or omega is small. If a large and small values of this omega, again, you can get analytical solutions, all right? Okay, but it turns out in practice that omega is also of order 1. It's neither large nor small, okay? And I went through that yesterday for the premixed flames, right? Okay, so now you can do a numerical integration of this structure. Right, okay. Again, this is I'm talking about this for small and large omegas, right? Okay, so that's the profile. So this is a solution of the inner structure. There's the profile. You can see that this is the profile of CH4, and you can see H. So H goes. This is a profile of H. Reaches steady state. So this is going into the oxidation layer over here. Okay, so you can see that H goes into steady state into the oxidation layer because if the gradients are flat, that means it is going into steady state. Okay, and it goes into the oxidation layer, and then the CH4 is completely consumed. Okay, so those are the profiles, right? Okay. So now So by matching, okay, by doing the entire matching the inner layer to the oxidation layer, and eventually matching the oxidation layer to the outer structure, okay. So we eventually get the scalar dissipation rate. So here this kind of outlines the procedure, okay, that one would use to get the scalar dissipation rate. So the point is, recall that going back to Tim's question earlier, that we have selected a value of the oxidized leakage. And this is the scalar dissipation rate that is consistent. So you can see here's the oxidized leakage. Okay, so you can see that here's the scalar dissipation rate, which is consistent with that oxidized leakage. Okay, so now if I plot the maximum flame temperature Tp, okay, as a function of the reciprocal, which is the scalar dissipation rate. The scalar dissipation rate is the reciprocal of a characteristic residence time, so that's what it's plotted against. Then you get the classical C-shaped curve, right? The top branch of the C-shaped curve is stable, okay, and the bottom part is unstable. So this tells you the critical conditions of extinction. So at this value of chi p, the flame is extinguished. Okay, that's the point. All right. Okay. Okay. Right, so now, so this is the oxidizer leakage. I plotted the oxidizer leakage. You can see that here in this case, the bottom part is the stable part for the oxidizer leakage. You can see that with the decreasing value, or rather increasing value, as you increase the strain rate, okay, this is the strain rate goes into, as you increase the strain rate, which is, then you can see that the oxidizer leakage increases. So as you increase the strain, there's less chemical reactions taking place, so therefore oxygen leakage is increasing through the reaction. So, and this is again, this is now the extinction over here. Extinction, right? Okay. So this is a final result. You can, so this is plotting the extinction strain rate or the scalar dissipation rate as a function of the mass fraction of oxygen. So what basically, so these are points are, so these are numerical points, the dots, okay, for detailed numerical calculations using detailed chemistry. And you can see that this is a line here, so S of order unity, so this is the asymptotic result. So basically asymptotics captures the numerical calculation fairly accurately. Okay, the important point here is that there's no adjustable parameters. All the rate coefficients that we have used are elementary rates. Okay, nothing has been adjusted. Right, so we are able to reproduce the flame structure. Okay, the critical conditions of. Okay. Okay, now these are just details. This is the flame, the maximum temperature as a function of the oxygen. Okay, right. Now this is this is an indicator. Okay, but I think what's more important is here. This curve. This is important. This is an important point. Remember that in the asymptotic analysis, we made the following assumptions. I said that epsilon is small, delta is small, okay, and epsilon is much larger than delta. Okay, so the point in asymptotic analysis, what one has, you make certain assumptions. You say that, well, you know, this is how it should be. All right. Then you can go through the mathematics. And then at the end of the mathematics is done, you should go back, okay, and check check whether the ordering which was assumed is correct. Okay. So this tells you here. Okay, this tells you the ordering. You can see that this is delta, and this is epsilon. So therefore, delta and epsilon. So the epsilon is much larger than delta. It's very good. But if you go to leaner if you go to very lean flames, then of course there is it's not green or rich. But if you go to very low oxygen concentrations, it turns out that both the fuel consumption layer and oxidation layers merge. So you can see that for these values, the asymptotics breaks down. Is what we say. Okay, so it's valid in this region. All right. But many times what happens is you make a set of assumptions. And once the asymptotic analysis is done, you'll find out, for example, it's quite likely that I would have found out that delta is actually larger than epsilon. Okay, that you can get that result. Okay, because there's nothing in mathematics which stops you. You know, you make an assumption, you can proceed. Nothing stops you from proceeding. Once you proceed and you find out that well, you know, this is not right. Actually, delta is greater. Then that means the entire analysis is wrong. So now you got to go back. Okay. And then redo the analysis with a different set of scaling. And once you get the scaling, something else will happen. I mean, you know, you find this quantity S is too large or something like that. Okay? Then you got to go back and redo the scaling. So generally, all these analyses take several months actually. So it's not, you know, it's not straightforward because every time you do an ordering, it's a lot of work. Okay, you get a result, you find the result doesn't work, you got to go back. Okay, so this is the result of many such with a lot of failures, so this is the final result of all those failures. So this is what works. Okay, so it's not very straightforward. I mean, you make an assumption, you get an answer. Okay, it's always okay. All right. So I think okay. Well, yeah. Here's the other thing I want to point out is that remember that we looked at one-step asymptotic analysis. Why that cases where the one-step asymptotic works. Okay. So the question is, why does it work? Now here's so here I show you that the activation energy asymptotic analysis, you get this result for the scalar dissipation rate of extinction. Okay. Now I can construct. I mean, what I can do is I can try to construct this is what, okay, this is what the results of activation energy asymptotics, okay. So therefore, so one can get okay, what I've done here, okay. So you can get from this result, okay, so you can get in effect, so if you take the logarithm of this, that's what that is, okay. So slope of a plot of E effective plot gives, so if you make a plot, okay, of this quantity as a function of 1 over TST, you get a slope, right? And that slope gives you the overall activation energy, right? So let's look at the, okay, next down. So this is a, so what I've done is taken the results from rate ratio asymptotic analysis, okay, and obtained from that a global one-step kinetics, activation energy for one-step reaction, all right, here. And this is, you extract from the numerical calculation. So in other words, here what that means is that you numerically calculate the flame, okay? So you know what this, so I know what the scalar dissipation rate should be numerically from detailed kinetics, okay? Then you go and try to obtain had I done this calculation with one-step chemistry, what would have been my overall rate, okay? So you can see that that's the overall rate. So you can see that, so here are the numbers. If you use rate ratio asymptotic analysis, I get an overall activation energy of 100. If you do an numerical calculation, this is what you get. And we have done experiments as well, okay, on critical conditions. And you take experimental data, and then this is what you get. So the experiments data, it gives you an effective overall activation energy of this. That's what I get from rate ratio asymptotics. So this is the reason why it works, because the apparent activation energy is large. So, you know, it's a combination of a lot of things, but the apparent, it just gives this apparent picture that it is large, and that's why it works. Okay. Okay. I think, you know, this is it. I mean, I'm going to, as I said, there's going to be change of pace. All right. I'm going to talk about some experiments. All right. So maybe I'll, okay. So I'm going to hold down. This is about, I just have a half an hour left. All right. So I'll hold down to, maybe I will ask questions at the end. Or is there any quick questions on asymptotics? Is there any? Okay. Or if it's not, let's, you know, so let's talk, I want to talk something about our work on surrogates, on practical, some practical work, okay, on surrogates of jet fuel. All right. Now, let's say why are we looking for surrogates? The reason why we're looking for surrogates, it turns out that the U.S. Department of and this is the point was that all military vehicles in the U.S. Should operate. The idea was should operate on only one fuel. Okay. For example, I mean, you have the Army as well as the Air Force and others. They should use for all their vehicles. They're supposed they should use only one fuel. Okay, and that fuel was selected to be JP8. Okay? So therefore, that's the reason for motivation for looking at combustion of JP8, which is a jet fuel. Okay. Now here's so that's just you know, that's just motivation. But then let's look at the approach. So the point is to look for how to understand the combustion of JP8, which is a practical field, right? Now the major components of JP8 are straight chain paraffins, branch chain paraffins, cycloparaffins, aromatics, and you saw a lot of this, right, with Ramsey's lecture. Okay, you have this very complex chemistry. Okay. Now one way, and Ramsey touched on this as well. One way to look at is to study the combustion of a practical field is to use surrogates, right? Now, why do you use surrogates? So in other words, if you want to understand the combustion of a JP8, you first select. How does one select a surrogate? What is a surrogate? The surrogates are mixtures of few hydrocarbon compounds. Okay, even though this is hundreds, there's only a few compounds. And then you want to select. You first have to decide what aspects of the practical field you want to reproduce. Okay, could be auto ignition. All right. Extinction or flame propagation, ignition delay. This is something you have to decide on first, okay? Then, once that decision is made, all right, the second step would be to, if you do an experiment, so you do an experiment with the real fuel and with the surrogate, right? You select a surrogate, you know, okay, and then, you know, just because based on what the composition is. Then you see how the surrogate reproduces what the real fuel does. Okay, so now you have a surrogate. Okay, but for example, if you want a surrogate to do flame propagation, it's not going to do ignition. Okay, so once that's done, then one develops detailed chemistry for that, more chemical mechanisms for that surrogate, and then you do a detailed chemistry, then you do reduced chemistry, and that reduced chemistry can be used in CFD codes. So the ultimate objective is to provide a set of chemical mechanisms which can be used in the CFD code, right, to predict whatever you want to predict. Okay, so that's the point, all right? So the point is, so again, I want to emphasize that if you have a surrogate that's picked for auto-ignition, it's not going to do, it may do flame propagation, okay? But you cannot expect it to do that, okay, because it was not developed for that, okay? Or now if you want to do flame propagation as well, then you got to put something else in the surrogate, make it more complicated, okay, right? If you want to reproduce everything of the jet fuel, you have to use the jet fuel, all right? So that's the point, okay? So here the idea is to develop a surrogate for JP8, okay? So at the end, I mean, my interest in that, or rather the Army's interest in was that they were looking at, they want to use the JP8 in their tanks, so therefore they were more interested in auto-ignition. So what I was focused on is to get a surrogate that can reproduce auto-ignition characteristics, which immediately automatically implies it's not going to do, extinction, it's not going to do flame propagation, but that's the overall goal, okay? Right. So we did experiments on counterflow configuration, where we measured critical conditions of extinction. We looked at soot formation. We did experiments on premixed combustion. We also did premixed combustion, okay, in the counterflow. And I'll tell you how that is. And we also did experiments what's known as Coflow. A Coflow is that you have a central tube and you oxidize on the outside, okay, and it's like a typical burner type configuration. All right. And this work was done in collaboration with Norbert, Peters, and Aachen, where they have developed mechanisms for some of the components of the surrogate. And we also looked at soot formation, right? But the soot formation work was mainly done in Aachen. And then the other one of the principal collaborators here in this work was Elisio Ranzi, who gave a series of very interesting lectures on chemistry. And this is a very powerful method, and that's probably the best method in the world to compute practical fuels. Okay, so he's probably only one of the few people who can compute practical fuels using simple mechanisms. Okay, so right. Okay, so now I'm going to show you some experiments. Okay, so these are the kind of experiments that we did. You have this counterflow configuration, right? You have, by the way, okay, so this is there are two jets flow towards each other. This is a pre-vaporized. So that means, you take JP, of course, is a liquid fuel. You take a fuel, then you pre-vaporize it, okay? And then mix it with again, as far as Army's application is concerned, they were interested in non-premixed ignition. Okay, that's the focus, okay? So this is, you have vaporized fuel coming from here. Air comes from the top. There's a flame that can be stabilized very close to the ignition point boundary layer. And then what we do is we increase the flow velocities of these two jets, okay? That's effectively increasing the strain rate until the flame goes out. Okay, so that's critical conditions of extinction, okay? So the point is now, again, you do this for different amounts of vaporized fuel in this jet, okay? And that was always air in our experiments. So now you get experimental data which gives you the strain rate the strain rate which is related to the flow velocities. So the flow velocities as a function of the composition. Then you get a curve. Then the point is to get you get a chemical kinetic mechanism that reproduces that. Okay. And this is an auto-ignition experiment. At the end of the class, I'm going to show a video of a typical experiment. All right. This is a auto-ignition experiment where you have a vaporized fuel coming from the bottom and heated. Now here the air is heated, so we can heat air up to close to 1100 or 1200 Kelvin. Okay. And then they come towards each other, and it's auto-ignition. So the flame ignites. Okay. So then. Okay, here, this work, as I said, was done in Aachen. They did some work on. So this is the. So this is the. Okay. I forgot. I used to forget. Okay. These are critical conditions of auto ignition. That's the That's the strain rate. Okay, that's the German for strain rate, and that's the auto ignition temperature. Okay, so this again these are again counterflow flames, right? Okay, so this is these are mixtures. This is decane. Now, it turns out that in Aachen they have developed something called a which we call the Aachen surrogate. So this is the green is kerosene. Okay, and this is the Aachen surrogate, which is made of 60% decade and 40% of trimethyl benzene. Okay. So this is this is the Aachen surrogate, 80% decade and 20% trimethyl benzene. So you can see that the critical condition of auto ignition for kerosene, which is JP8. So this gets very this particular mixture, which is the Aachen surrogate, reproduces that very accurately. Okay, right. So again, this work done in Aachen. This is the soot mass volume fraction of soot as a function of distance. You can see that this is for different strain rates. This is a soot volume fraction of soot, and you can see that the surrogate very accurately reproduces the volume fraction of soot as well. Okay, so this is our experiment that we did. Here you have so this is at UCSD. You have a counterflow burner, and then this is a typical auto ignition experiment. Here you can see at the bottom here, vaporized fuel mixed with nitrogen comes from the bottom. Okay. And this is our one important point that we have screens. We have many screens. And the idea of the screens, and that's very important to have these screens, because this screens ensures that the flow that comes out is plane parallel. So therefore, you obtain what's known as a plug flow boundary condition. Okay, and there are many experiments where you use these contoured nozzles. If you have these contoured nozzles, the flow that comes out of the contoured nozzle is not very well characterized. Therefore, it's better to use these straight drugs with screens. Okay. Again, this is a experiment for auto ignition, so therefore you can see that this is a heated coil, and then the air comes in, and the silicon carbide heating elements heat it up, and then you can auto it. So this is an experiment you can actually be running with auto ignition. Actually, the heated air is coming from the top. You can see it's glowing because it's very hot, the air that's coming out of it. Okay. Now what we did was before we did the work, we tested many surrogates. And here are the various surrogates that we tested. Again, this is for JP8. Okay, they're looking at ignition. These are all different compositions. Surrogate A, decane, methyl cyclohexane. Surrogate B is this. But this is another one that we tested, which is we call UCSD, 60% decane, 20% methyl cyclohexane, and 20% O-xylene. But you see, this is a very interesting surrogate because 60%, 20%. This is 60% aliphatics, 20% cycloaliphatics, and 20% aromatics. This is exactly the composition for jet fuel. Okay, that's exactly all right. And also, that is the high HT ratio is the same as that of jet fuel, right? And then we had a workshop on this, so someone suggested a particular surrogate that we should be looking at. So that was added. Okay, so these are this is actually the list of many surrogates, all right? And also we had Aachen surrogate, which is, it turns out that the two main winners are surrogate C and Aachen surrogate, which is 80% decane, 20% trimethyl benzene. The problem with that is, the only problem, which is not a serious problem, is that the high HC ratio is not that of JP8, okay? And there was a Drexel surrogate recommended in a Drexel, and there's a Utah surrogate, all right? Surrogate N1 and N2 came from Imperial College in London. All right, so all the surrogates were tested. Okay, that's a flame in our at UCSD burner. You can see that this is a typical JP8 flame. All right, so what's coming from the bottom is pre-vaporized JP8. Okay, mixed with nitrogen. It's coming from the bottom, and from the top we have air. All right. So you can see that we can stabilize the flame, it will stay there forever, okay? So now the idea is that you increase the flow velocities of these jets until the flame extinguishes, right? Okay. So that's the strain rate. Okay, so these are the different temperatures. T1 is always the temperature, because these are pre-vaporized, so therefore the temperature at which the jet fuel is coming is 473 Kelvin. The oxidizer is 298 Kelvin room temperature. Okay, so now this is the test. I mean, which surrogate is the best accurately reproduce critical conditions of extinction. Okay, so you can see all these surrogates were tested. I kind of ordered them such that there's a lot of depth. So this is the strain rate at extinction as a function of the mass fraction of fuel. Okay, there are many lines here. So the point is that I've ordered them such that if you put a line over here, that's the order. If these appear. So what the result of this extinction experiment tells us is that whatever we tested JP8. This is Jet A. That's commercial airline fuel. Okay, Jet A is a commercial airline fuel, and JP8 is the U.S. Air Force. Okay, with it's also that's what they use with some special additives. Okay, for high performance. Right. The point here is that if you look at so if you look at it, turns out that the ones that are closest is that to JP8. Okay, extinction-wise is the Utah surrogate. Okay. The next one was the Arkansas surrogate, and so this is the order. So this was the best, followed by the Arkansas surrogate and the surrogate C, which was developed. The other ones were pretty bad. Okay, but still these things are not that bad. I mean, if you look at, for example, if you look at the Arkansas surrogate versus Jet A, they're just still very close. We're looking at very small details. Okay, so really, I mean, in principle, one can say that so these are all pretty good. Okay, they reproduces extinction characteristics fairly accurately. All right. Now this is again I want to show, this is a so this is again these are experiments. These are used. So this is the fuel mass fraction as a function of strain rate. Okay. So these are experiments that was done at UCSD using the Arkansas surrogate. Okay, here you can see that, right? And the calculation. So these calculations are. So this is Eliseo Ranci's calculation using his detailed mechanism, lumped approach. So the point here is that, so this is for a given strain rate, the fuel mass fraction predicted by the numerical calculations are higher than the experiment. But these kind of errors are considered to be reasonable. I mean, it's not too bad. Okay, right? Okay, so that's there. You can see a comparison between experiments and detailed numerical. So we did the experiments, and he had this several thousand reactions which he computed, all right, and was able to do that. Okay, all right. Now here what I want to show you is that when you do these auto ignition experiments, since you want to develop since this has been using you're doing detailed numerical calculations with that, it's very important that the auto ignition always takes place at the axis of symmetry. Okay, so here this is a high-speed camera again at UCSD high-speed camera image of an auto ignition event. So what we have done is this is you can see the place. I mean you can see if you I'm sure all you guys have sharper eyes than I do, but you can probably see a thin so you can see the appearance of a flame. Okay, so if you when the right conditions are reached, now you can see that auto ignition starts here. Okay. And then pretty soon, once it ignites, the whole thing. So if you have a temperature, for example, here the temperature of the air is 12.1225 Kelvin. That's the temperature of the air that's coming from the top. So our experiments are so accurate that, but at 1220, or actually 1223, okay, you will not see anything. And increase it by 2 degrees Kelvin, and you will immediately see a light there. Okay. So that's a so this is accurate to plus or minus 2 degrees Kelvin. I won't say accurate, reproducible. Accuracy is a different story. Okay, but I can reproduce our experiments, right? And this is very important because often what you find is that in the experiment, if you don't use a high-speed camera, sometimes these things, there's insulation on the walls. You'll find a small some insulation breaking off. Okay, it'll come down. Once that insulation comes down, it'll ignite it. So unless you have high-speed camera, you cannot see that. Any dust particles will come from someplace and ignite it, right? So it's very important to look at these things using high-speed cameras. So the only data which we can see with the high-speed camera is recorded, right? Okay, so this is critical conditions of auto temperature, auto ignition as a function of strain rate. Now this is the key point here. You can see that this is jet fuel, JP8. And this is the pink here is the Arkansas surrogate. Now, as I said, our goal was to develop a surrogate that reproduces auto ignition characteristics, not really extinction. So if you look at the various surrogates that we looked at, the clear winner is the Auckland surrogate right there. Okay, right? And the surrogate C as well. It's also pretty good, except G. So these are the two. Both these surrogates are the best as far as autoignition characteristics are concerned. If you look at the relative order for extinctions are different. Okay, all right. Now this is again predictions by Elizio Ranzi. You can see that this is kerosene, which is the JP8. We call it kerosene. It's the same thing. Okay, and this you can see that autoignition for Aachen. I'm sorry, the Aachen surrogate accurately reproduces the autoignition characteristics of JP8, and these are numerical computations by Elizio Ranzi. There are some deviations, so this is not satisfactory how different they are. So there's room. So his mechanisms need to be improved as far as autoignition is concerned. But nevertheless, that's the data. All right. Okay. Right. So this is so this is like okay. Well, right. So it's yeah, pretty much the same thing here. All right. Okay. Okay. Now this is soot formation. This work was done in Aachen. You can see that. So this is a volume fraction of soot for the surrogate. Okay. You can see that this is and I showed before that experimentally the Aachen surrogate accurately reproduces the volume fraction of soot. And again, these are numerical calculations. At least the order is maintained very well. Okay, as you increase the increasing strain rate is in that direction. Okay, so the order is maintained. Okay, so this is again considered to be reasonable prediction. All right. So now the premix. So now this is all this thing I talked about was for non-premixed flames. We also looked at premixed flames. Here in the premixed flames, you have a so you have this from the bottom. Okay, I'm going to try to go. Okay, from the bottom you have fuel, pre-vaporized fuel mixed with oxygen and nitrogen. Okay, so it's premixed configuration. That's what comes from the bottom. Okay, and from the top we simply have nitrogen, pure nitrogen. Okay, so therefore this is a premixed mixture stabilized against the nitrogen stream. Okay, the advantage of this is if you do this, it's very difficult to do experiments on premixed flame which are because there are always these wall effects. If you do a like propagation in the tube or something, there are always wall effects that dominate. In this case, what you can do is you sort of push the premixed flame away from the wall. Okay, so it's easy to model that those kind of flames. All right. Oops. Okay. Wait a minute. Okay. Here. Okay. Yeah. So now there are so there you have so you have equivalence ratio. There's equivalence ratio phi, and so this is also an important parameter. So this is for example, YO2x is YO2 divided by this. But then this so if you have a mixture of air and the fuel, then this YO2x would be 0.23. Okay, all right. Otherwise, okay. So we obtain the critical conditions of extinction. Okay. So the T1 is the temperature of the fuel stream. T2 is the temperature of the oxidizers of nitrogen. So T2 is the temperature of nitrogen. All right. V2 is injection velocity. All right. So the experiments were carried out at T2 was 298, which is so the nitrogen came at that temperature. YO2x. So this is diluted air. Okay. The experiments with air would have a YO2x of 0.23. Okay. So therefore, there's excess nitrogen there, okay? And the temperature at which this came from here was at 473 to 483 degrees Kelvin. Okay, so these are because the pre-vaporized has a higher temperature, right? So here are the experiments in numerical. Okay, so here are the experiments. You can see that these are the pure fuels that we tested. So what is plotted here is the extinction strain rate. So again, I didn't explain the experiment. Here, what the idea, the point of the experiment is, again, we increase the flow velocity until the flame extinguishes, right? And we get the strain rate at extinction. So here you can see that this is the equivalence ratio and the strain rate at extinction. These are the pure fuels over here lumped up on the top. Heptane, decane, and dodecane. Again, these are all just experimental data. And here, these are all the aromatic fuels, which is O-xylene and methylcyclohexane, or trimethylbenzene, which is over here. And here in between is where the surrogates of JP8 are. For example, this is the Aachen surrogate, which is the triangle, okay? That's JP8, over there. and surrogate C. The point is that Aachen surrogate, even though it is, the point was, even though we had developed this Aachen surrogate only to reproduce critical conditions of auto-ignition, turns out that it also does a good job even at premixed flame propagation. Okay, so that's a bonus. All right, so that's pretty good. All right, and these are numerical. Again, this is Eligio's, Ramsey's numerical calculations. So you can see that this is so the symbols. So these are the experiments. Okay, so this is a well. Okay, so this is all right. Okay, so I'm just comparing. Yeah, these are the so symbols. Okay, symbols experimental data. So those are the experiments over here. Okay, and these are the green is numerical prediction from for surrogate C. We tested two surrogates. Okay, surrogate C and Aachen surrogate, right? So this is the blue is the experimental data for the Aachen surrogate, and this is the calculation from Ramsey's group. Okay, and then here is the experimental data from UCSD for surrogate C, and this is again the calculation from Ramsey's group, right? So what we established here is that the Aachen surrogate is pretty good, okay, and Ramsey's mechanism reasonably well reproduces many characteristics, ignition characteristics, extinction, as well as premixed flame propagation. Okay, so we did went further, and this was done. This work was done for the U.S. Air Force. We did Coflow experiments. Okay, experiments on Coflow in the Coflow configuration. Now you can see that the pre-vaporized fuel comes from the bottom. It goes in here, and this is a Coflow burner, and this is the Coflow air that comes from the outside. Okay, so now you can stabilize the flame in this particular configuration. Now the very challenging thing in this experiment was because the mass fraction of the fuel that enters is extremely tiny, very, very tiny. So how to properly design this part, this is the most difficult part, took us, it was very expensive. So we had this vaporizer, okay? This is a device, this cost over $10,000 to get this vaporizer. So this is capable of vaporizing very, very small amounts of the liquid fuel, okay? Because for Coflow flames takes very little vaporized fuel, right? So, right, so what are the measurements? The measurements we looked at was flame shape. How does the flame look like? Flame height. So we looked at flame shape, flame height, and we also looked at what's known as liftoff. Liftoff of the flame, okay, and reattachment. So you can see that as you increase the flow velocity of this mixture, or reduce the mass fraction of the fuel, either ways or both ways, the flame will lift off. Okay, then you can see under what conditions it reattaches. Liftoff is reattachment, right? So we looked at that. Okay, so this is where you can see that's the flame height measurements. Okay, just tells you how we did the experiments. Okay, I had a camera which was looking through that. Okay, height measurement. Okay, anyways, that's just some details of how the experiment was carried out. Okay, so the ones we tested was jet fuels was JP8, and this is some sort of a Fischer Tropsch which the U.S. Air Force wants to use, and these are surrogates of JP. The surrogates of JP8 is the Aachen surrogate, surrogate C, and we were particularly asked to test what's known as a SIRDOP. I'm not sure what the strategic environmental something. Okay, anyways, that's the surrogate the U.S. Air Force wanted to use. So the idea was they wanted us to do was to compare the SIRDOP surrogate with jet fuel, but we added these two things to it as well. Okay, all right. Now you can see that's the flame. So that's the photograph of the flame. So the Aachen. So I'm just showing the Aachen surrogate here. I'm not showing the others. Okay. So you can see that this is the Fischer Tropsch. Okay, that's the shell. Okay, so you can see one interesting thing is that this is the Aachen surrogate. You can see. So these are the conditions. I mean, this 8 millimeters. All right. Okay, so this is the flame height, and this is the jet velocity at which this comes out. Okay, you can see that the heights match pretty well between the Fischer Tropsch. It's pretty good match. Okay, between the flame height at similar velocities, the flame heights are pretty good. And here we can see, okay, so that's the point. These are just a comparison of flame height at different flow rates, okay, between the Fischer-Tropsch JP8 and the Aachen surrogate. Right, okay. Okay, so this is, okay, yeah, here, so these are for the different jet fuels. I mean, as I said, we looked at JP8, Fischer-Tropsch, and Fischer-Tropsch. So this is the plot of the flame height as a function of the, so these are the three different practical fuels we looked at, okay? And then next I want to show you is, so what's showing, oh, here's the Aachen surrogate comparison with JP8. Okay, you can see that the flame height as well as in function of nozzle velocity. So that's the, so you can see that's the Aachen surrogate, and that's JP8, reasonably good. Okay, so for Coflow flames, it does a good job. Now that's for liftoff heights for the Aachen surrogate, liftoff at point. So the idea is you kind of find out what flow rates it will lift off. You can see liftoff. So this is okay. Here, oh, sorry, I have to say I'm rushing. Okay, here the fuel flow has been kept at constant. Was constant. All right. What we changed was the composition of the fuel. You can see that at a fixed flow rates of the reactive mixture, when this is the mass fraction, when this is the mass fraction of JP8 at which the flame starts to lift off, and this is the mass fraction of Aachen surrogate at which the flame lifts off. That's a pretty good match, right? And then, so here you can show that this is like the liftoff height. So this is flame has lifted off, okay? Liftoff height here is 162, 165, and this is now what we are trying to do is we are trying to reattach the flame back, okay? And this reattachment occurs at the mass fraction 0.618. For the Aachen surrogate is 0.583. So again, this is pretty good. Okay, consider it good, right? And these are some summaries of the liftoff height and flame height and hysteresis. I'm going to go real fast because I want to show you a lot of other things. Okay, so that's it. So the Aachen surrogate. So that's. I wanted just to tell you how the Aachen surrogate was developed. Okay, you can see there are different tests: extinction, autoignition, right? Flame propagation as well as liftoff. Okay, and finally, I want to talk some recent work on high. So we have built at UCSD a high pressure apparatus to study ignition and autoignition characteristics of jet fuels at very high pressures. Okay, so we have we have something called a high pressure combustion experimental facility. And this combustion in this combustion experimental facility, we can do experiments up to a pressure of 2.5 megapascals. That's about approximately 25 atmospheres. Okay. And more recently, we got some funding to extend the operation of this device to 60 bars, so 6 megapascals. Now, it turns out that in this high-pressure combustion experimental facility, we can put many counterflow burners. All right, you can put anything, kind of spray, any combustion things we can study. Okay, so what we have done so far is that we have built counterflow burners to study gaseous fuels, liquid fuels. We have already built that and we have tested up to 2.0 megapascals. So here is a photograph of the experimental facility that we have. Okay, that's the counterflow burner. Okay, and they have these various viewports. So it's basically it's a cylindrical pressure chamber, and inside the cylindrical pressure chamber, you see a counterflow burner being placed inside the cylindrical pressure chamber. Okay, and these are the viewports. You can see the flame. There are 4 of them all around. Okay, and this is very interesting because for our counterflow burners, we cool them with water. So the water sprays in this thing. It goes here. Okay, and this was the toughest part of this is the toughest part of the design. Interesting thing is that this is all the exhaust gases that are formed are sucked through this. We pull it out. Okay, and it goes out into the exhaust, and then it's cooled and exhausted. So because we take all the products out, we don't have any fogging of the so none of the mirrors get fogged because they're always almost all very clear. because all the products of combustion are removed. The entire pressure chamber is pressurized with nitrogen. Okay, so we can go up to, as I said, we can go up to 25 bars, but this pressure chamber can withstand up to 150 bars, the pressure. Okay, so now here's some of the experiments that we did. We just studied hydrogen. So we looked at hydrogen, methane, ethane flames. Okay, we measured critical conditions of extinction. So we have this, hydrogen and nitrogen coming from the top, air from the air. Increase the velocity. And this is the strain rate. Okay, we measure critical conditions of extinction. Right. So this is I'm going to go through. Okay. So you said there's some of the accuracies. Okay, the experiments were over that range. Tells you what the experimental accuracies are. We measure temperature. We've measured temperature profiles also. Okay. All right. So that's the. So here are some measured temperature profiles in a hydrogen flame. And the symbols are experiments, and the lines are detailed calculation using the San Diego mechanism. You'll see that the San Diego mechanism does a pretty good job in predicting the temperature profile. Okay. So this is our critical conditions of extinction. So this is the strain rate as a function of pressure. So that's the. So these are the experimental data, and this is predictions of the San Diego mechanism, and that's predictions of the GRI mech. Okay. So what the shaded region means is that anything that falls inside the shaded region is good. Okay. So it's not, so the predictions are outside the shaded region. So therefore there are rooms for improvement of these mechanisms. All right. Okay. Now we did this is what we did look at methane, ethane, and ethylene. All right. So I just want to show you a flame. Okay, that is placed inside the pressure chamber. That's a ethane flame. Okay, 0.8 megapascals. So yeah.
Extinction data?
Yeah.
It's dropping with pressure? Is that right?
Yes.
Why does it go down with pressure? Because premixed goes the other way, right?
Yeah. It drops the pressure because that's it's because of the H plus O2 plus M reaction. That which is the chain termination step. That's the dominant reaction that causes the extinction strain rates to go down. Okay. So yes. But as I should show you that none of the mechanisms capture the experimental data. Okay, so for hydrogen, it's worse for ethane and methane. So I'm actually Eliseo and Foreman are actually working on that to try to improve the mechanisms. Okay. All right. Now I want to show you experiments at moderate pressures. Okay. Again, so these were experiments in that range for these things. Okay. Temperature profiles we measured, critical extinction and extinction. Here you can see this is the problem now. So this is the experimental data. As increased in pressure, the strain rate extinction goes down. These are predictions. So there's a significant difference between predictions and calculations. Okay, so even for simple fuel like methane and ethane, we got problems. It's basically the problem was this H plus O2 plus M, CH3 plus H plus M. Okay, all these three-body reactions are not. The problem with the three-body is the catalytic efficiencies of the three bodies are not very well known. That's why. So there needs to be a lot of revisions done on the mechanisms, right? So a lot of the present mechanisms don't work at high pressures. Okay, so that's ethane flames, right? Again, you see the same phenomena. Again, that's the problem. Okay, so I'm going to move on to. Okay, now the next thing. This is very unique. We are probably the only people in the world who can do this. Okay, right now, auto ignition. Okay, at higher pressures. As I say, I don't. It's really true. There's no one has data on auto ignition at high pressures. So this is what we have. See, all these fuels are liquids, right? The jet fuels, practical fuels. So when you pre-vaporize them, there's a problem because the increasing pressure. The boiling point goes up. Okay, so if you heat them too much, then of course you have breakdown. Okay, so we did experiments on the liquid pool. So basically, this is so in other words, this is the liquid pool. The fuel is introduced from the bottom. Okay, and this pointer tells you the surface how to maintain the level of liquid. So we actually look at that. make sure, this is visual, it's no automatic control, okay? But there's automatic control, we can change the flow radius of the syringe from very accurately, but so then you look at the tip, it breaks the surface that we know it's flat, okay? So this is a liquid fuel burner, okay, so those are igniters because this is, inside the high pressure chamber, okay? Okay, so now we do extinction, auto ignition, okay? So you can see that this requires lots of power because remember if you're flying at high pressures, air, and then so this is done. Heating is done with you have several leads. You have these are 4,800 watts silicon carbide heating elements. There's a ceramic heating furnace that goes around it. There are process heaters. I mean, you got many layers of heating. Okay. To do that, to get to the high temperatures, to do these auto ignition experiments. Okay, I'm going to show you a video of all that. Okay, that's the flame inside. That's a heptane flame stabilized inside the high pressure chamber. Okay, that's the 0.2 mega. So it's 2 bars basically. Okay, that's the flame. Okay, so these are extinction that we measured. I mean, as a function of pressure. We have not computed. We are not numerical. We have not done any numerical calculations. These are just experiments. Okay, so you can see that the strain rate at extinction is a function of pressure. It goes up, and there's a leveling off. Okay, of the extinction strain rates: heptane, cyclohexane, normal octane, isooctane, and decane. Now, this again, our aim, of course, is to to develop surrogates. So now you can see the surrogates. So these are the different surrogates. Now here, this is at Princeton University, they developed a surrogate. They use what is known as functional groups. Okay, it's a very, very interesting way to develop surrogates. Rather than, they just do that. They look at functional groups, how different radicals, what different groups there are. Based on that, they develop surrogates. Okay, so anyway, that is surrogate B. Surrogate A is the Aachen surrogate. All right. Now you can see that Aachen surrogate, so these are Jet A and JP8, and the Princeton surrogate is the best. Aachen surrogate is very poor as far as high extinction conditions are concerned at high pressures. Again, the Aachen surrogate was not developed to do extinction, it's only for ignition. Okay, so that's the claim, right? Okay, so this doesn't do very well here. Here we show photographs side by. There are two different events. I mean, this is on one side, this is JP8 flame at high pressure. That's the Princeton surrogate on the other. Remember, these are two separate pictures. They're not taken simultaneously. You can see how well the Princeton surrogate compares with JP8. In fact, if you look at here, it looks like it's even a continuous line, right? But they're two separate pictures put side by side, right? Okay, now these are so these are mass burning rate measurements. Okay, again. Okay, anyway, that's the flame standoff distance. Okay, so anyways, now the next thing I want to show you is auto ignition. So now we heat the air from the top and ignite it. Okay, these are auto ignition experiments. So now you can see again. You see the same thing. I mean, so this what we have here is a let's see, auto ignition event. This is normal decane. This is normal decane in the hyper. Okay, the normal decane at the pressure of 4.5 bars. Okay, close to 5 bars. Oxygen mass fraction, and the air that is coming in from the top is at 886 Kelvin. Okay, the fuel's normal decane. So you can see that now again you see it for the high-speed photograph. Again you see this very tiny flame that comes in around the axis of symmetry. And pretty soon, the big blob you see at the back is simply reflection. We have our ducts are being held with supporting structure. So this is just the camera, illuminating the supporting structure behind. This is the flame right there. Okay, so this is just a reflection from the supporting structures, and that's the but this is the key point. How the flame looks after it auto ignites is not a consequence. Okay, the start of the event is what is important to us. Okay, so that tells you. Okay, here are some data that we took. This is temperature as a function of pressure for different fuels: heptane, decane, and dodecane. That's the data here. But this is very interesting. You can see that as you increase the pressure, the auto ignition temperature decreases. Okay, that's one. Second, what's also interesting is that for a given value of the pressure, dodecane has a lower auto ignition temperature then decane as well as heptane. So this means that, I mean, this is very interesting because it means the autoignition is taking place because of low temperature chemistry. Because if you have low temperature chemistry, decane will be faster. The higher the longer the chain, it has ignite more quickly. So you can say that all these autoignition events are influenced by low temperature chemistry, and this is a very new finding. This is something we just submitted to the International Symposia. This is not known. Okay, the influence of autoignition. Okay, and then this is JP8. Okay, JP8 Jet A that we looked at. Different. These are commercial fields. Temperature decreases with pressure, and then again, here's the Aachen surrogate. Okay, the Aachen surrogate. And then you can see that Aachen surrogate accurately reproduces the auto. So Aachen surrogate is again a winner here. It's not the Princeton surrogate is not nearly as good. Okay, the Aachen surrogate, which was designed for autoignition experiments, does a very good job in doing that. Okay, right. Okay, these are some concluding remarks. So the point here is that the Princeton surrogate is good for extinction, but the Aachen surrogate is good for autoignition. All right. Okay. Now this is just very recent, happened like just before I came here. This is you can see that these are numerical calculations by the Ramsey group experiments. Okay, our experiments, and therefore again a very good agreement. Again, from the numerical calculations, we have concluded that low temperature chemistry is important for autoignition. Okay. Now I'm going to show you typical. I mean, if I have 5 minutes, I want to show a video. Okay. So this is what, as you go on, what you're going to see a typical. So first, what you're going to see is we will show you the burner, Counterflow burner. Okay. Without the without the high pressure chamber. Then you see the Counterflow burner. Then the high pressure chamber will be lowered because it's very, very heavy, massive and heavy. It's going to be lowered with a crane. Okay. We're going to lower it down. Then it attaches. Okay. Then I'm going to show you a typical how we do an extinction experiment and an autoignition experiment. The extinction experiment, what you do is you would just, of course, the pressure is completely controlled by pressure regulators. At some selected, so what we would do is that we will just, at some selected value of the strain rate, first of all, the computer will set up the conditions, okay? Some strain rate and so on, oxygen mass fraction. Then we turn on the syringe pump. So then the syringe pump is turned on, the liquid fuel flows into the high pressure chamber, and then you adjust the flow rates on the syringe pump such that the pool is level, okay? And then you give a command for ignition. So then you see this is all totally automated. Then the computer will give a command. Then the igniters will come in, okay? Ignite the flame. The flame is established. Then you change the syringe pump such that the flow rates are again controlled, okay? So to make sure that the flow rates and the burning, so the level is constant. Then I want you to observe the pressure readings. You see how the pressure, there's a computer will show you what the pressure is. You see that the pressure fluctuations are very, very small, okay? That means we can very accurately maintain the pressure. And then automatically the computer will start increasing the flow rates, okay, until the flame extinguishes and the data is recorded. Okay, that's what you're going to see, right? So that's what that is. Okay, in the autoignition experiments, the same thing, except that now you have a pool of liquid fuel. Air comes from the top, okay, and you keep on increasing the temperature until autoignition takes place. Okay. Okay, can I show the video? Okay. Yeah. So that's why maybe I'll pause the video at a few points so that maybe is there volume here? Okay. So
You want the volume?
just likely, okay. Oh, it's not here. Okay, it's not there.
No, you can.
Very, very little. Okay, it doesn't show up there. Okay. It's too large in here. Okay, that's okay. Yeah. Okay, this looks good. You can do the full screen. Okay. Or maybe you can turn on the lights a little bit. Okay. Yeah. Okay, you can start again. Okay, there you go. So you can see that's it. Or make it stop, pause that for a second. Start again. Okay. I think that's enough. I think that's enough. Yeah.
Yeah. He'll be fixing for the volume.
No, that's okay. It's okay. No, not necessary. Here. So you can go back because I want to show the start from the beginning. So now you can see, let me see if I can pause that. Can you pause that? Okay, yeah. Okay, you can pause that. Okay, now I can, now I can go, okay. Then I can stop right there. So here you see the counterflow burner, okay. So that's the bottom part of the duct, the top, the exhaust system. Okay, the entire counterflow burner, the entire burner. So these are walls. I mean, they're made of plastic. The entire thing is enclosed. So the entirety is enclosed. Okay, so these are very high impact poly. I mean, you could actually, what we were told, that you can stand outside and shoot a gun on it, it won't break. Okay, the idea is that if you have an accidental explosion, okay, okay, let's move on. Lower the volume. Yeah, look. Okay, good, lower. So you can see that's the pressure chamber. Okay. On the top. Okay. That's the high pressure. So that's the pressure. So the entire thing is going to be okay. So that's the. So we're going to show some extinction. Okay, now you can see that's the counterflow burner. Okay, so we are establishing the conditions. This is the computer controlled strain rate, oxygen mass fraction. Everything is controlled by the computer. Now, so that's the liquid level adjuster. Okay. That's, you can see the igniters come in. Okay. That's the flame. Okay, that's the igniter. Okay, that's the. What we're doing the extinction. So now automatically the strain, when it comes over there, you can see that the strain rate is increasing. Okay, there. And you watch the pressure, very little fluctuation of pressure. We make it very accurate control of the pressure. So now the flow rates are increasing continuously, and you will see the flame extinguish. So flow rates are continuously increased. Okay, so the strain is going up. Watch that. Oh, there you go. That's extinction. Okay. The flame is gone. So now we record the data, the extinction point. All right. Okay. So that's all the extinction strain rate, the oxygen mass fraction, all that is recorded. Okay. So what they do is they shut off the fuel, flood it with nitrogen, so that everything is gone. Okay, now I'm going to show you auto ignition. So now it's ready to the second experiment. So that's the auto ignition. So again, this is liquid pool. Yeah, okay, that's the air is coming in. We can't see the temperature there. It's over here. Okay. Oxidizer. Hard for me to read that. But anyway, that's the oxidizer. Temperature is over 1,000 Kelvin, close to over 1,000 Kelvin. That's you can see that very little fluctuation. Okay. That's the pressure. Okay. Then you can watch. Then the temperature is increasing. The temperature of the air will continue to increase. Then you suddenly see a flame. Oh, there you go. The flame is ignited. Okay. So now you record the data. So once the flame ignites, it's a little bit. So the reflection you saw was really the stuff back there. Okay. So yeah. Okay. The data is recorded. Okay, that's it. Yeah. Thank you.
Any questions? Hold on just 1 second. Speak to the mic.
Sir, the surrogate properties, especially for atomization, Weber numbers, that is surface tension and viscosity, how does it compare?
I mean, that's a very good question, because there are two types of surrogates, something called a chemical surrogate and a physical surrogate. Okay, a chemical surrogate only will reproduce the chemical properties. You're not. See, the idea is to develop a mechanism that can be used in the computer code. Okay, so the point is, the Arkin surrogate has not been tested for surface tension or the physical properties because that was not the aim. It is not that we wanted to run the Arkin surrogate in an engine and see how it performs with JP8. The point was just to develop a chemical kinetic mechanism for the surrogate. So it's just the chemical surrogate.
But any study is made, how does it compare? No.
No.
Okay.
In fact, most likely the study is not necessary, and if you even do that, it will probably fail because it will not.
Okay. Another one, how does it compare the temperature, the flame temperature per se, the surrogate and JP8?
I mean, you see, that we have not measured flame temperatures, but I would expect they're not that different because the heat release rates are similar, okay, and extinction strain rates are the same, so one would expect that to be similar as well.
Sir, one more question.
Yeah.
That is, the auto ignition temperature decreases corresponding to pressure.
Yes.
But what is the mechanism? Probably you can explain, because if you see the activation energy, it is not a very highly dependent function of pressure. It's a temperature function.
I think that's exactly the question which Tim asked me. What it is that because this is one-step chemistry, this is real chemistry, correct? Not no longer one step. Turns out that the three-body reactions, H plus O2 plus M, all right, that depends on the pressure. So that is the chain breaking step, all right, and that the rate of the chain breaking step increases with pressure. So the chain, so therefore that's the reason why it goes down. Okay.
Okay, sir. Thank you.